Okay, in this video we're going to be talking about rational exponents. So let's just jump in and review a little bit about some radicals and square roots before we get started. So remember that we most often deal with square roots or just the radical that looks like this. But we can also have roots that are bigger than 2. So a square root is a root of 2. Remember, it means that there's like a little invisible 2 sitting right here. We can have bigger roots like a cube root, right? And we've seen those in past examples. And we're just going to remember that this little 3 right here is called the index. Okay? And the index just tells you what root you are taking. So all the same rules that we have already learned work when you're dealing with roots that are bigger than 2. So if you are multiplying radicals that are the 4th root or the 5th root, you can do it the same way that you did before. You do get some differences when you start simplifying roots of a bigger order or roots that are bigger than 2. So remember that when we were simplifying square roots, we were looking for twin factors. When we're simplifying cube roots, we're looking for triplet factors. When you're simplifying the 4th root, you're looking for quadruplet factors. Basically, the root tells you what size of group you're looking for when you're simplifying a square root. So let's just take a couple looks at examples of what it would look like to multiply some of these roots together. So remember that when you are multiplying, you still need to make sure that you have the same index number. So you can't multiply a cube root and a square root together. You can only multiply cube roots and cube roots together, square roots and square roots together, 4th roots and 4th roots together. So with A, we have the cube root of 3 and the cube root of 9. So we can make that the cube root of 9 times 3, which is 27. And then we can simplify that into 3 times 9, and 9 can be simplified into 3 times 3. And then, since we're doing the cube root, we can look for trio pairs. Since we have one trio of 3's, then we can take that out of our radical and we're just left with a 3. Okay, let's work through B as well. So with B, we multiply the 2 and the 6 together, so those outside numbers together. And then because we're dealing with the 4th root, and both radicals are the 4th root, we can do 50 times 25. And that 50 times 25 is 1,250. Okay. And then we're going to want to break the 1,250 up. I'm going to break it up into 50 and 25. 25 breaks up into 5 and 5. 50 breaks up into 5 and 10. And then the 10 breaks up into 2 and 5. So now, since I'm dealing with the index of 4, I'm looking for groups of 4. I see a group of 4 5's. So the 5 gets to come out of the radical, and then I have to leave the 2 in there. So 5, 4th root of 2 would be our final answer with that one. Okay, so we're going to work on, the next section has us identify if these are like radicals or not, which we kind of already did in the last section. So we'll just kind of zoom through it pretty fast. Remember that a like radical means that both the index and the radicand, or the number inside the radical, are the same. So in A, I have this 4th root of 2x and the 4th root of 2x. So yes, these are like radicals. In B, I have the square root of x and the cube root of x. So here in the second radical, I have the index of 2. And in the first radical, I don't have an index, which means the index is 2. So since these indices are different, these would not be like radicals. Okay, in the next examples, we're going to look at how we would add or subtract these radicals together. So remember that if the index number and the radicand are the same, then we can add the radicals together. So in A, we have the 4th root of 5 plus 3 4th root of 5. So my radicals are the same because the index is both 4 and the radicand is 5. So what I'm going to do is I'm going to add the numbers in front of the radicals. Remember that there's a 1 in front of this first radical. So I end up with 4 4th roots of 5. Okay. I'm not going to work through the next example because it's going to take a little bit and it'll be really good practice for you. But when you first look at B, you don't see any like radicals, right? You have the cube root of 54, the cube root of 16, and the cube root of 2, so they're all different. However, what you're going to want to do is you're going to want to simplify all of these radicals down, and then perhaps after you simplify them, you will have like radicals. So I'll let you guys practice doing that one on your own. Okay, now we're going to jump into multiplying radicals and radical expressions. So our steps here are, number one, we have to distribute appropriately. And we'll see some examples of that. But distributing just means that we have to multiply everything together that needs to be multiplied together. Okay? Okay, the next step is that if the radicals have the same index, multiply them together. And the final step is to multiply constants and the numbers out front of the radicals. Okay, let's take a look at some examples of that. So let's look at A on the next page. The cube root of 6 times the cube root of 3. So here, if I'm going to think about distributing, all I'm going to do is multiply these two together. I just have two things to multiply. Step 2 in my steps for multiplying radical expressions is that if the radicals have the same index, we can multiply them. In this case, the index is 3, so I can multiply these together. So I would get the cube root of 6 times 3, which is 18. Okay. Let's jump over to example C, because I want to show you one that has a little bit more intensive distribution. So our first step is to distribute appropriately. So I'm going to do a similar thing as what I did in A, but now I have the square root of 5 minus the square root of 6, all times the square root of 7 plus 1. So I need to make sure that I multiply the square root of 5 to the square root of 7 and to the 1. And then I have to make sure that the square root of 6 gets multiplied to the 7 and to the 1. Okay. So let's just start with the square roots of 5. If I distribute the square root of 5, it would be the square root of 5 times the square root of 7 plus the square root of 5 times 1. And then I'm going to be multiplying the negative square root of 6 times the square root of 7. So the minus square root of 6 square roots of 7. And then the negative square root of 6 times 1 would be negative square root of 6 times 1. And then I can just go through and simplify each of these small expressions. So the first one would be the square root of 35 plus the square root of 5 minus the square root of 42 minus the square root of 6. Okay. And again, I want to look for like radicals. I don't see any. I could try to simplify out the simplify the radicals throughout here. I don't think these ones simplify. These ones are not going to be able to be combined at all. So that would be your final answer. Okay. One word of caution is when you see problems like you see in E, it's really tempting just to take this squared and distribute the squared into both of the terms. You cannot do that, okay? When you see something like E, you have to rewrite this as 4 square roots of 3 minus 1 times 4 square roots of 3 minus 1. And then you can go through and do all your distributing and make sure you multiply everything together. Okay. I'm going to let you guys work through the rest of these examples on your own. Just make sure you're following the steps that we talked about before. Here's the next big thing we need to talk about. What we're going to be doing now is we are going to be comparing radical expressions to exponents. So if you remember back at the beginning of this unit, we were talking mostly about exponents, and then we jumped into radicals. So here we're going to make the connection between the two ideas. So looking at this first sentence right here, if n is a positive integer greater than 1, then the nth root, so when n is the index of a, if it's a real number, then a to the 1 over n is equal to the nth root of a. So basically this is just telling us, here's the big takeaway. That's a lot of big words, but basically the idea is that if I have some exponent with a fraction, a to the 1 over n, I can rewrite that as a radical where the index is n. So let's see an example of that. Say I have a to the 1/3. I can rewrite that as the cube root of a. Okay, so the bottom of your fraction here and the index are the same. And then the big number or the base of your exponent and the radicand are the same. Okay, so let's work through a couple examples. So the first step in this next section is we're going to rewrite all the exponential expressions as radicals, and then we're going to simplify them if we can. So 25 to the 1/2 would be the same as put 25 underneath the radical, and there should be a 2 on the outside. Now remember, we don't usually write the 2 if the index is 2. We just make it the square root. And we know that the square root of 25 is 5. Okay, let's look at b as well. So I put 64 underneath the radical, and then since 3 is the denominator of that fractional exponent, that becomes the index. Okay, and we can simplify that as well, which we won't do right now for sake of time. So we have to be careful when we see ones like c, okay, because we have this entire expression, xy squared z raised to the 1/6 power. So when we go to change that into a radical expression, we have to put that entire thing, the xy squared z, underneath the radical, and then the index is going to be 6. So again, I'm matching up that 6 right there with this 6 right here. Okay. Let's jump down to example E. This one is a little bit different. So we have to be careful with E. E is different than C because in C, the x, the y, and the z were all raised to the 1/6 power. In E, only the x is being raised to the 1/4 power. So when we go to write the radical, we're only going to put the x in there. Okay, and we'll put the 4 right there because it matches up. And then this 2 out front, it just gets to stay out front. There was no exponent on to start with, so it won't be in any sort of radical at the end either. That looks very different from F, which is super similar to E, except for now the 2 is being raised to the 1/4 exponent. So when we write that square root, or that 4th root, we're going to have the 2 and the x inside of there. Okay. So now let's do a couple examples of working the other direction. So we've done some practices where we've taken expressions with fractional exponents and changed them into radicals. Now let's change some radical expressions into exponents. So this first one, we have the 7th root of 2xy. That's going to be the same thing as 2xy to the 1/7. Okay. This next one, b, is going to be the same thing as the fraction ab cubed over 7 to the 1/4. Okay, I'll let you guys keep working through the rest of these, and you want to just be super comfortable switching between the radical expression and the exponential. Okay, now we're going to get a little tricky on you. Sometimes we are going to have exponents inside of radicals. Okay? And if that's the case, like say we have, well, let's talk about the fraction version of it first, I guess. So say I have a raised to the m over n power. Then I can convert that to a radical, and the bottom of my fraction is still going to be the index. Those are going to be the same. And the top of my fraction is going to be an exponent that's going to be on the a. Okay? Now the cool thing about converting between fractional exponents like this is that you can either put this m inside the radical or you can put it outside of the radical. Okay, so let's see what that looks like. That'd be easier if we work some out. So if I have a to the 2/3, then if I want to write that as a radical, then this 3 is going to be the index, and the 8's going to be inside, and the 8 is going to be squared. Okay. I could also write it where I have 8 as the index, so I have 3 as the index, 8 as the radicand, and then I'm going to think about squaring that whole thing. And there's different reasons why you might want to choose one or the other of these representations, but the important thing to remember is that these two expressions that I just circled in yellow are equivalent.